So I actually did most of my development at home on my box there. And then of course this morning I bring it in to try and get it working on my laptops. And one laptop which seemed to be able to record stuff quite nicely kept on freezing up. And this other laptop, which has a little slow atom, wouldn't seem to work the program in terms of recording at a fast frame rate. So I decided to go for the slow atom that actually didn't freeze up. We'll see how that goes. So I'm actually a lecturer in this department, or the Research School of Computer Science, and my research area is high-performance computing stuff. I have a background in symbolic machine learning. I sort of look at how to, I guess, do physics-type simulations fast, and we've been looking at GPU cards and stuff like that. So my area really isn't multimedia. However, I do have an interest in multimedia, and I often record my lectures, and I've been using various tools for that. And I guess one of the main tools I've used for that is Record My Desktop. But I sort of wanted to do something a little bit fancier than what Record My Desktop did, so I can sort of record some of my face talking, and also that I can use the camera to show something on a board or give a demo. So I can sort of integrate between what Record My Desktop does and a webcam. And I found what I could do, I could run Cheese and bring that up and use Record My Desktop with Cheese, but I'd get all these latency issues between the audio and the video, which was unsatisfying. Also, I played around using Cheese, and I also found latency issues. So underneath Cheese, there's GStream, and more about this format than myself. And also, I was sort of a bit uncertain where to sort of pitch this in terms of what people's background is. So I sort of want to give a bit of an idea of what goes on in these video formats and their containers, and then look at the Clapper code and explain how I've used sort of just the standard libraries to weave together my program, and some of the problems I had along the way. So we'll look at what's motivated me, which I've sort of gone over. We'll talk about why video is hard, because it's quite big. We'll look at these audio-video formats, look at container formats, why you can change from RGB to YUV type models or colour models, how frequency domains can save you a lot, reference frames, motion vectors and encoding. Then we'll have a closer look at inside Clapper and how that works. Okay. So I did a little bit of testing on the various available webcam recorders. So Cheese, FFmpeg, AVConv, which I guess seems to be a bit of a split, and also using Record My Desktop. And I found various latencies between the audio and the video. One thing that I found was interesting, about 2 weeks ago, I thought, oh, let's try Cheese again, and it worked beautifully on my desktop, and I go, oh, maybe I should have just stuck with Cheese and used GStream. So I think there's a talk later on by, is it Tim Ansell? Yeah. That he'll probably be able to do what I've done in many nights at home in a few script lines. So, but anyway, we'll see how we go. But why don't I just do a quick demo of it? So this is the moment of truth. So if I run the program, no, we're a pretty small room, so if you want to stop and ask questions, please feel free to do that. Also, if someone can tell me when I'm running out of time, would be good. So, just running it with no input, and it's now recording. So if everyone could say cheese, cheese, or no, actually say Clapper. Ah, that's right. This is my slow atom. Here we go. We'll try that now. So everyone say, oh, get it around the right way, Clapper. Clapper. Okay, let's see if that worked this time. It's not perfect, so and we'll run it through mPlayer.
You misspelled OGB
First time round, out.obg. So can you kind of hear that? Anyway, I don't know whether we can see. So that's actually not too bad, I guess, in terms of the sequencing, because I found it varied a lot in terms of the synchronization of the audio and the sound. But one thing I was playing with last night to actually make sure that synchronization is better is actually using a clap to do that, because I had problems with getting information out of Pulse Audio, but more about that later. So if I run the clapper with another option, -W, oops, out.org, get the name right this time. And now, if I do an actual clap in front of the camera, I can then forward backwards to get where the clap is exactly, and then I go start, and it starts doing the recording, and now those two are actually synchronized for the recording. So that's my makeshift approach at synchronizing at this point. I think I'd probably like to move away from that and explore how I can get better timing information out of Pulse Audio. Yep.
I think they do actually do similar things when you're recording concerts and things. They use a drum beat or something where they've got a visual reference,
Yeah.
audio reference, and then they sync on that and use that.
Yeah.
Same thing for the clappers.
Yeah. I guess that's where the name comes from, the old-fashioned clapper, where they'd synchronize the audio and the video. I mean, I think we should be able to do better than that, because all the information, the timing information, is there somewhere. My problem is I find audio extremely complex to deal with. I mean, I found the video stuff not too bad in terms of getting timing information, but the simple Pulse Audio interface I've been using, the latencies don't seem to be accurate, or when I take account of the latency that Pulse Audio is giving me, it doesn't seem to make the audio and video line up properly. So it's something I'm doing wrong, but that's sort of something in progress. But at the moment, I'm going to stick with the clapping, and I can synchronize those audio and video for my recordings. And over the next semester, I'm actually doing some recordings for my teaching. So rather than record during the lecture, I'll actually do some recording of the lecture prior to the actual lecture. And I've been using so far my bit of software. The other thing that I've been playing with is actually capturing what's on from the X window. So if you have a look at that there, you can see it capturing what's on X and redisplaying it. So my little display is actually half the size, and it means that I can do, demos and typing, and it sort of combines, if you like, what you get out of Record My Desktop with a webcam recorder, and you can sort of change back to the camera at various stages and stuff. Okay. Anyway, that's a quick demo. Let's get back to some of the theory. So as I was saying before, video is big. You may have thought there was a lot of jelly beans in the jelly bean jar, but that's nothing to how much storage video will take up. Although I guess it's not as bad as it was when you didn't have as much storage available. Let's take even the simplest standard definition television, which you have something like 720 by 576 pixels, and you normally have that at 25 frames per second. So you can imagine just storing one frame using a raw video, so storing the RGB separately, 8 bits for R, 8 bits for G, etc. So 8 bits for each of those channels. Multiply it out, divide by 8, you end up with about 1.2 megabytes of data. So that's not too bad to store. But you do a second of that, you multiply by 25, where you end up with 30 megabytes. You take a minute of that, you get 1.8 gigabytes, and if you do an hour of video at this rate, you end up with about 108 gigabytes of data. So you're going to fill up your terabyte hard disks fairly quickly. The other issue with that really is how fast can you stream out to your hard disk? Now, if you look at current hard disks, you can stream out at about 100 megabits per second. So you could do that. You could stream straight out to your hard disk, because if you're recording at this rate, you'd end up with 30 megabits per second that you'd have to push out to the hard disk. So you sort of can just do it with a modern hard disk. But that's standard definition television. So you can imagine if you went to high definition television, or more resolution or more frames per second, you're going to be pushing the limits of what your hard disk can do. The other thing you might have thought, well, what might be a bottleneck is actually pushing it out to memory, but that actually turns out okay, because memory is about 64 to 170 times faster than what you can push to a hard disk. So you don't really have trouble pushing your data out to memory, pulling it back in, etc. for processing. You've got plenty of time for doing that, which is good. The other thing is modern CPUs seem to be able to handle the processing of video without too much trouble, which is kind of nice. What about going to audio? If you go to audio, things are much better. If you had 1 second at 16-bit audio, often you'll sample at 44,000 hertz, you would end up with 86 kilobytes, which really isn't much in modern storage. Or if you went for a whole hour, you'd have 302 megabytes of data. So also isn't too bad, but you're starting to get bigger files. You wouldn't want to have to record a week's worth of audio. You'd start having quite large files. So in both of these situations, you really want to be able to compress this data down and store it in a smaller file, which will enable you, I guess, to store more video, and also, I guess, extract it apart more quickly. So some very smart people, and some of them are here, have worked very hard of working out ways of actually squashing this video down. And if you look at the different formats, if you go to, say, FFmpeg and do minus formats, and we'll do that now, so just FFmpeg minus formats, you'll see a large range of different possible codecs, some for audio, some for video, some for containing either audio and video, and they all have their different characteristics and compression ratios. And also there's quite a large sort of legal dimension to all this. So some of them are encumbered with patents, some of them aim to not be encumbered with patents, but there might be a submarine patent there. So there's all these sort of interesting legal issues. I guess for what I've focused on, because I'm quite interested in open source, I've tried to focus on formats that I don't have to worry about that I'm pretty sure are unencumbered with patents. And I guess that's why I've gone for the OGG format. Probably in the future it looks like the WebM seems to be the direction people are going with, I guess, open source type formats, but I guess we'll watch and see how that goes. Okay. So you can imagine video and audio are really very different beasts. They're very different types of data, okay? You've got a fairly slow frequency in terms of frame rate, but you've got lots of information in each of those frames. The other, you sort of have either mono or stereo, but a much higher frequency, but not much information in each of those samples, if you like. 1 or 2 dimensions in each of those samples. But when you join them together, you want these two very different beasts to join together nicely. So it makes sense to have some sort of container format, a format that contain any type of stream. And we see that with OGG. So OGG's a container format. It doesn't specify what type of video or audio you put in it. You could put FLAC, RAW, some Vorbis, or you could put all sorts of different types of video formats. But it enables you to sort of combine those streams together. Now, I'll just go to my diagram. So you can imagine if you have a stream of video data coming along, the stream is actually broken up into little packets. I'm bound to get all the terminology wrong here, so excuse me if I do. So you can imagine all these packets coming along. We've got time moving, say, in this direction. We've got our packets coming in. Normally the beginning packets will contain header information. How big is this video? What sort of sampling are we using? What sort of quantization? All this sort of information. So that might be a special few packets at the beginning. Now at the same time, travelling along in time, you've got the audio data moving along. Now of course, this will possibly have different packet sizes. Maybe it's got a whole lot more, etc. And so what your container format has to do is combine these two streams together into one file format, and you want that file format to not have a sort of large overhead. You don't want it to cost a whole lot of data for just combining these two streams together. So you want it to cost, maybe 1% or something. But you want to be able to combine it together, so when you then play the audio and video later on, you can pull it back apart again and play it separately. And so OGG does that, and so in OGG you have these things called pages. So there's beginning of stream pages, so you might put, say, in that first page, the first packet for the video. You might have then another page that comes along. It will have header information. We'll put the, header information for the audio in there. In these OGG pages, there's a serial number for the particular stream. So we'll give the serial number, say, 2 there, 7 there. So in here we've got a 2, and here we've got a 7. I should have picked something else. 2 and 7 are too hard to distinguish. And then as you go along, you get more of these pages which contain the different streams. Now OGG has, each page can have more than one packet, so you can put more than one packet in one page, but all those packets have to be from the same stream. So maybe in this next one we'll put, say, the audio here, and there might be a few packets of the audio within one page, but it'll be all that one stream in that one page. Maybe the next one along here will have a packet of the video. Sometimes these packets are too big for the pages, so these pages have a limited size, in which case the packets can spill over into the next page. So I'll draw another page and I'll sort of show that. So say we have another one here. Actually, I'll just draw another page. So all these have some header information in there, some error correcting. Is it error detecting or is it correcting code in the pages? Error detection, just error detection. Yep. And we'll put, say, one packet moving over another page. Okay. The other thing that is put in these pages is this granule number, which is sort of a sequencing number that is defined by the stream. So the stream says, this is where we're up to in our stream, and that sequencing number has to go in increasing order. But the OGG container format doesn't really know about the meaning of that sequencing number, but it requires your sequencing number to be increasing, so you can't have them going the other way around. And the other thing is, the sequencing number sort of associates with the time of the packet in the stream. And so the audio, it uses what sample you're up to for that granule number within the page. The video does something a little bit trickier, where it divides it up into the frame and a sort of an offset from the frame. But when you're combining these two together, so when you're putting out your final file, you have to make sure you interleave them correctly. So in time, you don't have a whole lot of video, say, coming at the beginning, and then a whole lot of audio that comes later, because that will cause chaos for your player, because it gets all these frames, and it doesn't have the audio for them yet. So you need to, when you put them together, you need to order that correctly. And that was one issue that I had in terms of the code. Okay. So what tricks can be used to reduce the size of these images? One is moving, say, from an RGB format to a YUV format. So, firstly, our eye makes things much simpler for computer graphics and, I guess, for storing these video, in that really colour is an infinite dimensional space. You can imagine you can have different intensities at different possible frequencies. However, because of the cones within our eye, we really pick up sort of these three different types of colours, okay? And so pretty much on an RGB monitor, if you reproduce a combination of those three colours, you can fool your eye into believing just about any colour. Although, of course, some of the more prime cut, like the more single frequency colours, you miss out on in that. Anyway, but that said, our eye is much more, it seems that intensity is much more important for the way we perceive stuff. So colour is sort of secondary compared to how we perceive the intensity of an image. So if we spend more bits conveying the intensity information over the sort of what colour information it is, we can actually get a better image for the amount of bits that we spend. Okay? And so that's sort of the first trick that's often used, where you modify the RGB into this YUV model, and Y is sort of intensity. So you can imagine if here's our RGB cube, and you've got colours sort of sitting anywhere in the cube, if you put a line straight out from the middle, coming out, and that's sort of intensity, how bright a particular pixel is, if you store that, and then you have other dimensions that say what colour it is, you can put more bits into the intensity compared to the colour and get just as good an image. And you'll find actually the data that's coming out of the, these little webcams is actually in YUV format by default. So often when you want to display it, you need to do that translation from YUV to RGB. But let's just clear that and I'll show you how that often works. So imagine we've got our image, it's just a raster image, we've got a number of pixels, maybe we've got 4 pixels at the top. If we were just storing that in RGB, we might have R0, G0, B0. So that's taking 3 bytes for that 1 pixel. Okay, then we do another 3, and another 3, etc. So in the end, we've got 3 times 4 bytes, 12 bytes to store those 4 pixels. So if you take a YUV format, what would often happen is you take that pixel, work out the intensity, how bright it is, and you store that. So you store, say, Y0. Then for that pixel, you also work out its colour, how much sort of bluey or greeny there is, and you can store part of it, let's say U0 there, and we'll store the V0 there, and then we'll store the next intensity for the next one. And so now we have Y1, Y2, Y3, and U2, and V2, okay? And so what it means is that these adjacent pixels can have different intensities, but they share the same colour. So you see this in artefacts in images, where you see, if you have an image that might have some text in it and you have a clear border, you'll see this shadowing type effect on that clear border where it looks like it's the wrong colour. And that's partly because of this. But it means that storing that image, instead of 12 bytes, you've stored that in 8 bytes. So that same image. And for natural images, ones that you get out of webcams and the like, you won't really notice the difference. You sort of get more bang for your bit, bang for your buck, or whatever. Okay, I'm running out of time, so I might move quickly through some of this. The other trick that is often played is that you transform the information into a frequency domain rather than like a spatial type domain. And I've got a little program which I've written, if I can find it. Here it is. Okay, so imagine if we had 200 values that we wanted to store. Okay, we have 200 values we wanted to store in some sort of graph. We could just store the 200 values directly. So 200 by, if we store as floats by 4, we get 800 bytes to store those 200 values. However, what we can do is we can change it to a frequency domain where we integrate, sort of multiply every bit and add up the value between, say, that shape and a straight line, and just send that average across. We also could say integrate this funny shape with this curvy line and send the amount across, or store that amount. We can integrate this curvy line with our signal we want to store and get an amount. And then what we can do is just store those 5 amounts. So rather than store all 200 values, we store the 5 amounts that's in this sort of frequency domain. And then we've saved a whole lot of space. And we can take those 5 values and multiply them by these shapes and return something that's sort of close to the original value. Okay? So we've actually saved a whole lot of data and we've got something that's pretty much the same. And so that technique gets used in, say, MP3 type approaches for compacting the data down, because you know the very high frequency stuff you don't hear anyway, so you may as well not store that information. But also it gets used in Theora or JPEG, where you do that but over an image. And I'll show you sort of how that happens. So there's some pictures of different JPEG images stored at different levels. JPEG and also Theora separate it into the YUV type values, and you end up getting your image, breaking it up into little blocks of 8, and then for each of those little blocks of 8, you store that in this sort of frequency domain rather than just as the values of the pixels. Okay, and if you have a look at this sort of grid here, this is like our these shapes that we're integrating the image against. So we sort of integrate the image against just getting its average. We integrate the image against one that's sort of a curvy in that direction. We do it against one that's a curvy in this direction, etc. So we get a value for each of these amounts, and that sort of moves it into the frequency gain, and the compression or the gain is made by not storing or quantizing at a very low level all these high frequency stuff. So you only really store information about sort of the lower frequencies, but you lose something, but in terms of how you visually perceive it, it's pretty much the same. So that's one trick. The other trick that's played is, you can imagine in a video, the frame often doesn't change much from one frame to the next. So as you have a sequence of video, it doesn't change much from one frame to the next. What you can do is you can store a vector that says how it changed from the previous frame or from a keyframe. So you store that vector, and then you have some residue where you store as a difference. And that can save you an enormous amount of data. Once you've done all that, usually over the top of that is some sort of standard lossless encoding, say Hoffman encoding, where you look at what happens frequently, and you use a smaller string to store the things that happen frequently. I guess the devil is often in the detail. If you want to have a play with the Clapper webcam recorder, it's open source. It's under LGPL, and you can get it here. So you can download it there. It's got the current version at the moment. I'm just about out of time. I'll quickly just say a few things about what's happening inside it. So in Unix, everything's a file. So often when you deal with stuff in the system, you deal with it via a file. And images from a webcam are really no different. You have a special file, So here's this video, actually it'll be video 0, I think. Here's our file, if you like, that we talk to get the video information out of. So basically you open up that file, you need to have permission to open up that file, and you do these I/O controls to sort of set up the webcam. What I've done, I've used mmap, so I mmap parts of that file into the space of my program, and then I can get the data straight out of that. And from that, I can then transform it into wherever I want and store it. Pulse audio is my great frustration. If you look at the interface for it, I've used a simple interface, and it's very simple, but I had a great deal of trouble getting timing information out of it. And when I've tried to use the more complicated interface, it's too complicated for me. So I'm partly thinking, do I want to move to, what's the other one, Jack or something like that? But then it's not a standard Unix, Ubuntu sort of thing, and anyway. I've used the standard libog, libtheora, libvorbis. If you go to the Xife website for that, is that how you say it? Xif website for that. It goes through the steps you need to do for constructing these and saving them, etc. I basically just followed those steps. I got the video data ready, I pointed it to the right thing, I said save it away, etc. So really those libraries do all the hard work. Care was needed to get the audio and the video to interleave properly. That was one issue that I kept on having. Also, I thought the audio would pace the situation very nicely, and I'll just use one single thread, pace it with the audio, store the video as I went, modify things to get the latency right. Didn't work at all. I found the audio would tend to come in these batches. So you'd say, give me some audio, and Pulse Audio would just delay for quite some time, and suddenly it says, oh, I've got some for you, and it just gives you a whole lot as you give it buffers to fill up, and then it stops for a while again, which wasn't very good for getting the audio and video sort of synchronized nicely. So what I ended up doing was having a thread that got the video at a nice rate, put it into some buffers, and then I had the main saving thread that got the audio as it was available and used the video from the buffers. So it meant that I had to synchronize those buffers using some semaphores. I also had I also had the main thread that did the GUI. So I used Glut, and it just sat in the background doing the GUI. What's next? Maybe WebM. Wouldn't mind having a go at moving it to that. What's his name? Brooks always says, you always throw away your first bit of software and start again. Clapper at the moment is my first bit of software. I probably need to throw it away and start again in a way in terms of refactoring the code, now that I understand what I'm doing. Need to really work out this whole latency issue. It's not too bad doing the clap, but I'd rather get away from that and actually get the information directly from the hardware, or get the information somehow from the hardware. Maybe get GPUs to do some of the heavy lifting. There's some generalizations that really need to happen. I've limited it to just one resolution. Get the mouse pointer working for the image capture. Work out why Totem doesn't want to play my OCV recordings. MPlayer works quite nicely. It kills over when I give it to Totem. Maybe do something interesting with animating webcam to images transitions, so I can have the image of me sort of coming up and then or the image of the thing going down. Maybe even doing something that enables me to do a little bit of post editing. I think I've actually gone over time, so I apologise for that. So I'll hand over to you.
No worries. Thank you very much.